The next session will be conducted by Felix Petriconi with There is a New Future session. Felix is working as a professional programmer since 1993. After he had finished his study of electrical engineering, he started his career as teacher for intellectually gifted children, freelance programmer, among others, in telecommunication and automotive projects. Since 2003, he is employed as programmer and development manager at the MUIS Medical Solution AG in Bremen, Germany. He is part of a team that develops and maintains radiological medical devices. His focus is on C++ development, training of modern C++, and application performance tuning. He is a regular speaker at the C++ user group in Bremen, a blog editor of isocpp.org, a main contributor to stlab.cc, and a member of the Accus Conference Committee. Maybe you don't know that Felix in 1996 started his career with the development of database applications for a German Ministry of Environment. In 2000, he developed for Ericsson real-time tests for UMTS and SIGMA, mobile network speech transcoders. And since 2003, he's working for MUIS as a development manager and senior software engineer in Bremen. The team he is working with develops and maintains a medical device to display mammography images for breast cancer screening, diagnosis, and therapy. So everybody, round the applause for the speaker.
Thank you very much. Wow, it's hard to see you. Thank you very much for coming to my session. And thank you very much for the conference organizers to accept my proposal to speak to you. So my bias already was described in my introduction. If you want to reach me somewhere, you can write me an email. I have a website where I blog occasionally, and I'm a little bit active on Twitter. So the C++ language is too large for anyone to master. This is not for me. This is so everyone lives in with the subset. So what I show you today is my subset. So what I know. So and if there is anything what you think that I'm incorrect or it's wrong, please come to me after the session. I will and correct me so that I can learn something too. And this one, Sean Parent said this 2012 at CPP Now. So if he says that one cannot know everything about C++, I think I'm in a good place. So why I'm here? We use many cores in the standard computers to distribute tasks or work so that we gain the performance. And I learned that it's pretty easy to make lots of mistakes, and it's quite hard to maintain this kind of code. Then in 2015, I listened to the CPP cast with Sean Parent, where he talked about concurrency, and I was really impressed, and I said, well, I want to learn more at this point. So I started a collaboration in his open source project, and it's really fun to work there because I learned a lot. And I really like sharing my knowledge and bring it to you. So, some questions to the audience. Why are you here? I try to see you a bit. Who uses stud futures? Wow. Who uses boost futures? Okay, a little bit less. Anybody using the stlab futures? Nobody. Okay. So, and everybody still thinks that he or she is in the correct session when you're talking about futures? Good. So why do I have to talk about concurrency? The free lunch is over. Who coined this term? Herbst, that's correct. And it's quite a while ago. It was in 2005. So what does this mean? Can anybody in the audience tell why is the free lunch over? Or did we had a free lunch before that time? Yes, what does the free lunch, what does this quote mean? Yes, the point, he said the single thread performance. So up to that time, the CPU manufacturers were very helpful and helped us developers a lot by adding more transistors and increasing the CPU speed over each generation, and we didn't had really to care much about how we write our code, because on the next generation of processors it will run faster. This stopped around this time, where the frequency more or less was stable. The CPUs cannot go any faster. Can someone explain why they cannot go faster? Sorry? Well, physics is a big area. Can you be a little bit more specific? Yes, but I think they're putting the transistors are going smaller and smaller at the moment. Where I think we're about something about 10 or 15 nanoseconds structures. So they are pretty good at making the thing smaller, even today. Clock speed, that's a very important point. What's the problem with clock speed? Why not increase it anymore? Yes. So at that point, if you increase the clock speed, the power consumption goes not in a linear manner anymore. And that means that you have a real problem in getting the thermal energy of the CPU away. So they couldn't put any more, couldn't increase the CPU speed anymore. So they put more cores on the same die. And so now the problem is on our side because we have to use them. But there's always this but. There's Amdahl's law, which says that in this formula that the speed up is somehow connected with the number of synchronization between the different operations and the number of cores. So in an ideal world, we have on the bottom line, we have the number of cores, and in the top line, we have the speed up. So if we double the number of cores, we have speed up. We double the performance. Great. No, why not? Yes, so let me rephrase it. So in certain amount, you need some kind of synchronization. And even if you don't think that you have to synchronize, your machine is synchronizing. So even if you're doing a synchronization just of 10% of in your complete machine, you just go on this line. And as more cores as you add, as it worse it's going to be. You have 20%, it's not going better. And you have 90% synchronization, you have nearly no performance gain. So we have to fight against Amdahl's law. How can we use multiple cores? So one thing is we use individual processes. They are single-threaded, and so there's no interaction, one might think. But even if you go with this paradigm, you are not on the straight line of Amdahl's law. Why is that? Even if you say that, he said that because of operating system calls, that's true. But under the assumption that you don't have to call OS calls because you have everything already done, and then you start the calculation. Yes, cache. So memory bandwidth. So this is your synchronization point, and there are hardware out there so that each CPU has their own memory, but not on the custom devices that you and I normally use. So a standard PC or your mobile device, all of them has one main memory, which is then used by all the processors. So even if you go this paradigm, individual single-threaded processes, you don't have real linear performance again. But the next thing is probably you want to you can as well you could go multi-threaded in one process without some kind of synchronization. This is pretty much the same as the one before, but then most of the time you have some kind of synchronization between the work which is done on the different cores. And then you come to the point that you have to synchronize. So these are the typical primitives which the most of the languages gives to you. So you have mutex, atomic, semaphores, memory fins, or transactional memory. Even we don't have this so far in C++. But all of these, I would call them low-level synchronization primitives. And but that's what I want to bring to you, is that you can use higher-level abstractions so that you can really avoid all these low-level stuff, which makes your life much, much easier. So some of them are futures, channels, or actors. And I want to talk about today about the futures and the channel. So, small introduction into futures. What is a future? You have a function, f, and this returns a result, r. And the future separates them, both of them. So, sorry. And so when the function is called, then later the result of the function, it might sometimes later, appears in the if the function is executed, then the result will later appear in the future. And this is not a new technique. It's pretty old, from the end of the 70s. So what can we do with the future? With the future alone, you can pretty do nothing. Future is so whatever you have to do, you compose them together. So one of them is a continuation. So you have a function that calculates something, then you have a result. This result is then passed as an argument to the next one, and so on. So an alternative is that you do a merge. So you have two functions, they independently calculate something, you have a result, and this result is then passed as argument to the merging, to the next function, and later the results comes out of it. Then another way of composing is a split. So you have an argument, or you have a result, and you want to pass this to two different instances in your application. For instance, one is going to bring something into the UI, and the other thing is storing something on the disk. So, and next one, property, I think it's very important. It's cancellation. Have the exam that you have this kind of graph of task and futures. So, and by sudden, the user is not interested anymore on this result. So then there's no reason to calculate it anymore. But at this point, so there's no need to wait for the arguments of this task. So that means that we can drop these two results as well. So and then the complete graph collapses to this. This is a property, I think, or many other things are as well, is very, very important. So let's see what we have. The C++ 11 standard introduced futures. And they were added, it's a little bit funny, but they were added in Boost 1.41 in 2009, which is before it was standardized, but there was a standarding proposal for the standard, and then later on there was implemented in Boost. But the later development of the features are based on what is currently available in the Boost. So, short overview of the things we have in the standard. So, we have something which returns or calculates as the answer to everything. And since, I don't know, hopefully many have read the book Hitchhiker's Guide to the Galaxy, the calculation might take longer. So we do an async operation, and the std_async returns a future of int, and then we hopefully do something meaningful in the time, and then later we access the value out of the future, and we would print 42. So as well, this was an example of a void task. Of course, you can do this with a task that takes an argument. For in this case, I just pass a string. It stays with the return value. At this point, we have to create a package task. We extract from the package task the future, and we pass the argument to the task. And again, we get the result of 42. Everything clear so far? If not, please ask now. Good. Sometimes bad things happened. So we're on the way for looking at the answer. The Vorgones appeared, and this is very bad because then you have to listen to their songs or to their poetry. So at that point, when we try to get the result, we get the exception thrown, or this exception is thrown, and we have to live what we got. Okay, now we have a problem. What is the biggest problem in this code when we want to do best CPU utilization? Beside that, these are just dumb examples. But I wanted to highlight. Yes, he said we are waiting. That's correct. Well, do we wait always or just sometimes? Sometimes, yes. We wait as long as the future is not fulfilled. So, and currently in C++, there is no direct way to ask if the future is already fulfilled. You only can do it with the wait for member function and provide a 0 timeout. Then it immediately tells you is the future already there or not. Okay, so what do we have with the futures which we have so far in C++ 11, 14, and 17? So we don't have any kind of continuation. We have no merge. Split is missing. We cannot cancel it. It can be modeled, but it's really complicated. And we have no join or automatic reduction. So if your future of future is your result, then it would be nice if it automatically joins to a future of t. We have no progress monitoring, which might be interesting. If you have a certain amount of operation, then you want to see at what time or which step you are within the monitoring process. You cannot provide your own executors. So where the task should be executed, you have to rely on that what your library implementer is giving to you. And as you already said, it blocks on destruction. So you really have to wait until the future is fulfilled, until you can destroy the object. And future of .get has a problem that it blocks, as we already said, and this can lead into nasty deadlock situations. So this is not a way I want to program. And of course, they don't behave as a regular type. So then let's have a look into boost futures, which are further development of futures. So they support the continuation. So this is realized via a .then. So first you do your first calculation and .then, and then you do the next one. Let's have a look how this could be done. So we have still our heavy task, which will be calculated, and then later on we want to report the result. So we compose, first we create our future of get the answer, and then we create the continuation, and we tell, and we say that the answer should be reported. Then we do something else, and we get a result. Okay, better. Then we have merging, so you can do a when all or when any. When all means that you get the continuation is triggered when all the results are there. When any means that whenever the first result is there, the continuation goes on. So let's have a look into an example. So we split up the heavy calculation, and we create two futures. We move them into the when all. And then we create the continuation, we extract the result, add the sum of both, and then we wait. And at this point we get the same result, of course. So, trick question, what is the type of F? What, please? A tuple? Yes. A simple tuple or tuple of futures? Is it more? Yes. It's a future tuple of futures. So if you write it, you get this one here, which is, from my point of view, rather complicated. Okay. Let's see the capabilities of the boost futures, or which is similar to what comes with C++ 17 in the TS. So we have continuations, we have merge, but the next stuff is all missing. Boost supports executors, but all the other stuff is not possible so far. And there's a problem that the C++ TS, it lives in an experimental namespace, and the they does not work very well together. I'm sorry. So, but there is a new future, and you can find it on this website, and we are on GitHub. And I want to introduce possibilities of this library. So we do continuations, we do the when all, we have support a split, cancellation, the automatic reduction. At this point, this were not there so far, but we want to improve there. We support custom executors, and of course, we do not block on destruction. And we behave as a regular type. We have a certain amount of dependencies. If you want to use C++ 14, we need boost optional. And if you go for C++ 17, you have no additional dependencies. So let's have a look. You need some kind of includes. So again, we have our task that we want to perform. And I just scroll a little bit up so that we can see the bottom of the code. And And we have our own async, which takes as a first parameter an executor. So this is the instance where the task shall be performed. For instance, the default executor is the thread pool, which on Windows, it uses libdispatch on macOS. And for Linux, we provide our own thread pool implementation. So, and then as another parameter, we pass the task that should be calculated. And this then returns a future of int at this point. Then we have to, then you, so this is just for illustration, but don't do this in your code. This is kind of busy waiting. So this is busy waiting as long as the result is there. So this is not the way as you should do it. This is just so that this the code of this slide really compiles, works, and terminates correctly. So if there's a result, you can call it, and you get the output. Okay. Because users requested it, we support something like a blocking get. But we make it really obvious that this is a blocking in your code. So you do not make any kind of progress when you call this function. Okay, and this blocking get is, of course, not implemented in polling. So, of course, we support error handling as well. So we have our task which got interrupted. We have our normal creation of the future. We do our we wait as long as the result is there, and in this case, the result is an exception. So this is rethrown on, and we catch it and we proceed. Okay. So next interesting thing is how we do the continuation. So we have our task. We want to report it. So after the task is fulfilled, we want to bring it to the user. We create our future, and then we pass the then we pass the continuation. So, and the big difference is because report the answer takes the argument by value and not by future. So this is then a call by value. So it's much easier to bring this together with, for instance, existing code. Okay, and then you have this result. So this looks a little bit complicated because, but I wanted to show you how this join works. So in the middle, you have an expression that returns a future of int. And this gets passed as an argument to a continuation. And from this is a continuation to our starting point. So without this join, the result would be a future of int, which is not very nice if you want to compose a bigger graph. And so this library automatically reduces it to a future of int. Okay. So as well, since we don't pass the argument to the continuation as a future, this is not the way as we propagate errors. And at this point, we have our problem, or the task that reports the error. Then we have something that is capable of handling the error. And or which accepts a value, and then this one is which is capital. And so we have our task, and then we do not a dot then, which is a normal continuation, but we offer the possibility to recover, and in this case we accept the future which comes from here, and then we are capable of extracting the error, and we can continue from there. Okay. Yeah. Okay. Then the other one example of a merge. We have two different futures, and we pass them into a when all. We provide our default executor, and we have our task which takes two arguments, and we pass the arguments into the when all, and of course we get here now the same result. Okay, now we come to the new stuff which is not available so far in Boost or the 17TS, which is a split. And this is just a continuation on the same future. Let's look into an example. We have our default, we create our first future, which returns us the answer, and then we want to report it to two different instances. One is to Arthur, and the other one is we wanted to report it to Marvin. And at this point, the original future is then we do a continuation in the one direction, and this is a continuation in the second direction. And so that this compiles, we have to do blocking get on both, and we got a result from both. But this is not very nice. What could we do instead? Yes, we can join them. It's true. So that's the same as before. So we do when all of these two futures, and when they are both fulfilled, then we're done. Okay, and latest we add Coroutine Support. So this is available on Clang compiler and on Visual Studio 2015. So you can create, you can have a coroutine that returns future of our library and proceed from there. Good. Small thing for executors. As I already said before, executors are needed to specify where your task shall be done. There could be there could be thread pools, serial queues, but often you want to, after a certain computation was done, you want to update your GUI or your user interface. And most of the UI frameworks that I know don't allow direct update from a different thread than the main thread. So you have to provide an executor that then does the execution in the main thread. Yes, the executors, that's a problem. So far, we don't have them in the standard, and there currently is heavy debate when we get them. They're currently meeting in San Diego, and hopefully we get some executors with 20, but that's not done so far, perhaps just in 23. In Boost, executors derive from a common base class, not in our library. Here you just have to provide an object that implements the functional operator, and that's all. And so these are the executors which we have so far. So just a little example how to do this. This is not code which really works. It just should illustrate how it works. So you have a line ended somewhere in your UI, and you did a calculation and you want to update it. So first you have the execution, which is done on a background on a thread pool, and you add a continuation, but here you add a different executor or scheduler, and this is something which you could provide, and this then executes the task in the main loop, and then it's legal to update, for instance, in this line edit of Qt. Okay, I had this talk before, and somebody came to me and asked, what does it gain? Is there some kind of performance benefit of doing this? And I did some measurements in our application. So what we do? So in our medical application, we have to compress the images in a proprietary format so that we decompress it much faster as the images as we got them. And in the very first implementation, we used threads, which so for each slice that we or each stripe of an image that we wanted to compress, there was a thread was spawned, the calculation was done, and the thread terminates. And well, this worked fine, but at a certain point we got complaints from the customers, and we noticed that at least on Windows, it sometimes can happen that the creation of the thread might take up to 1 second. So fast things are not possible in this way. So what do we see here? On the bottom line is the number of stripes. So a single image is divided into many stripes. And on the vertical scale, we see the compression time. So in the old implementation where we used user threads, we got about this kind of performance increase when we increase the number of stripes. Yes or no? We wanted to reduce the overall time, and we got this kind for user threads. And then we did the same by using a thread pool, and you see it got faster, and at a certain point it's not going slower again. And another very interesting thing is that the variation is very big. So this is a real absolute max and min time for those calculations, and you see that the variation on by creating user threads is enormous compared to the variation that when you use the in this point the Windows thread pool. And probably you can identify the number of cores the machine had that I used. Any idea? Correct. Because at this point, it takes more and more time, and you have contention of the different threads that were running in parallel. So I did the same with bigger images. So this is now an image of this size, and here are they are much closer together, but the variation is still very big. So at this point, the transfer of the pixel data to memory is come to much more into account. So if you have small tasks, I really can recommend don't spawn for small tasks each time a new thread. It's very, very bad from the performance point of view. Okay, what do we want to do more? Some kind of optimization. Okay, so let's recap. Futures are, I think, a very good way to structure your code, and you can then do all the calculation with minimal contention. But this kind of graph, what you can create, is just a single execution graph. So it's a one-use only graph, because after the graph is fulfilled, you cannot do anything with more. You have to create a new graph. And at this point, channels close the gap for multiple invocations. And I want to do a short introduction of channels. So you can, as with futures, you can graph of execution, but it allows to it allows that you pass more than one value into it. And they were published by Tony Hoare in '78, a great book I can really recommend. So how you can make an image of a channel. So it's, I imagine it as some kind of pipe. So on one end, you send values into the pipe. And at the end of the pipe, we put something which we call a process. So you can do a certain amount of calculations on the values. And this is then at the other end is the receiver. So let's have a look into the code. We have a sender and we have a receiver and we tie them together. So then you have created a minimal kind of channel where you can pump values into it. And you specify an executor where this value should be, or where the calculation should be done. And this is just a very simple example. We just want to print the values which come out of the, which we pipe into the channel. So we have our receiver and we pipe, so we concatenate the printer to it, and we have a resulting process which does the printing. Then we have to set ready so that we can start the calculation. Then we just send a certain amount of values into it. And yeah, and then we just simply wait until all results are there. Of course, again, this is just a primitive example. It was just want to illustrate what you can do with these kind of composition techniques. So, of course, we can realize a split as well, and this we do. You have to pipe. You have to use twice or more times the pipe on the original receiver. So at this point, we create again our initial channel. So we attach two printers. So this is the first one and the second one, and then we send the values into it, and then you get your result. If you have questions, please. Yes? No, it does not. That depends in which order they are printed. Pardon? Yes. This is so. The first process prints process A and the passed argument. I think it's there, but it's round about here. I'm sorry. It's a huge screen, but it misses the bottom line. Sorry. Okay, then we support merge as well. So we have different kinds of merge. So we can do some kind of zip or round robin or whenever how the values come into it. I'm looking a bit into the time. Then you have possibilities to specify the buffer size, and you can attach an executor to all your steps into your graph. But these are examples I do not want to show here. But on the documentation page of the library, there are examples for this. Okay, then we have the problem that sometimes the processes which you can attach into the graph, they come with state. And some of the problems have an end-to-end relationship. So if you send one value in, but you want to generate two of it, or vice versa, you just pass two values in and that should be combined and you just have one. This cannot be done with the simple with the symbol lambda, for instance. And then there's other things is when do you proceed if there's no value coming down the stream? How you should proceed? How do you want to do some kind of error handling or something? And all this, we need a different kind of process that you can attach. And for this, you have to provide a process which follows this kind of structure. So there is no kind of base class that you have implement, but you have to provide these kind of functions. So the await function, that is this function that takes all the values that comes from upstream and that you want to process. So yield returns the value of your calculation, or you have to implement it that it returns the value. And then you have to provide a state, so then the channel knows when to proceed, if it should wait for more values or if it should yield the next one. And optional, you can pass, provide and close an error if certain problems appeared. Let's look into an example. I will come to this later, to this small adder. First, we create our channel, then we pipe our adder to it, and at the end, we want to print result. So, and then we do the following. We just create this small loop, and whenever the user has entered a number, we send it into the channel. Clear so far? Okay. Then have a look at the process that we attached. We have a sum. So this process should add up all values that the user have added. At a certain point, it should print the result to the user. So we have to remember all the intermediate values. At the beginning, we wait forever, so we are expecting new values. And whenever we are called, we add the value to our sum. And just to make it simple, as soon as the user has entered a 0, then we say, okay, now we print the sum what we calculated so far, and we go back to the beginning. And then the machine, if our state is yield, then we will be called immediately with yield, and then we should better return the result of our calculation, and then we are ready to begin from the beginning. This is just a very, very primitive example what you can do with this kind of processes. Okay. So the channels, as a conclusion, the channels closes the gap where futures just allow single execution, so you can do multiple executions on the values, and with the combinations of split and merges, you can create bigger graphs for image processing pipelines or different things of calculations that you might need. My takeaway for you, don't use mutex, logs, or something like that. Use futures, channels, or others, for instance, actors, to use the available CPUs on your machine. Yes, there's a question. Yes. Yes. Yes, there are plans. There are plans to do this. And if you have questions, then don't hesitate to yell at me, because I don't see probably the first 3 rows, but then I just have, you are in the dark. There was a question. What do you mean a join operation that's blocking? Yes, I can go back. Or this sounds like a bigger question. Welcome. I think you can. You can do a when all. You can combine all the futures which you are doing calculations, and you do a when all, and then then you can do a continuation on when all things are done. Then you continue. Okay. Then there was a question. Yes.
Okay, so my question is, in all your examples, you showed that when you do the receiver pipe sender, you store the result in a local variable, but you don't actually use it. So is it like, you have to save this temporary object, or?
Yes, otherwise it destructs. If you
so it's not like the receiver is keeping a copy or a reference to the sender, to the
no, you have to. If you build up the graph, you have to hold the last ends. So not the things in between, but you have to hold the last one. Otherwise, the complete graph will destruct itself.
So it's constructed externally. Okay, thank you.
Are there plans, or is there a way to handle dynamically changing graphs? So say I have a graph and something changes in my system and I want to add a processing step and I don't want to rebuild the entire graph. Is that possible? So because you always had this set receiver ready or something like that, and then only then did it start processing?
Yes. So that's a point where you cannot change it anymore. That's the current design. If there are requests to change this, then we might think of this. But at that point, you come to some kind of synchronization question. When really should this happen? Or it adds an overhead inside the graph for additional synchronization that we would like to avoid. Okay. More questions?
Thanks. So there was a picture of a graph. There was no ending. Like you said, there's no need to wait for some values, and it was you remove some nodes.
Yes, I can go back to this.
Yeah, that's the point.
Let me see.
That's on the beginning.
Here.
Yeah, this one. Yeah.
Yeah.
So it was really not covered in the doc, right? This cancellation. Like
It's covered implicitly. So the point, if you destruct, for instance, I don't. It's not working anymore. Sorry. So if you destruct this one, so if you remove, if you destruct this, then this completely will collapse. But this is not something I have add on my slides. That's true. But what should I show in this point when there is nothing? That it's.
Is it somehow related to the thing like someone asked if you don't receive the value, like you do not return, then it collapses and destroys it?
Yes.
Something like this. Okay.
Yeah. So let me see, where was there some? Okay, that was the point. So use high-level abstractions that eases the development of your code enormously. If you don't try to handle around with mutex, locks, and all this stuff, it's much easier. Don't try to invent your own thread pool if you don't have to. Use something which comes with the operating system. They're highly optimized, they're directly connected to your kernel, and they get performance that you will never get if you do it by your hand. And if your operating system, for instance, Linux does not have a thread pool which comes with the operating system, then use one which is really optimized, and don't try to invest into this. It's probably the wrong side.
Do you maybe know if any kind of standard library implementation uses actually system thread pools? Because
Yes.
Default run policy or default execution policy on STD-async is something like spawn threads until you can, and then defer those tasks. So
it's not, I think it was at the beginning, but I know for Windows they use they do the execution on the Windows thread pool.
okay.
And on Mac, I don't know. On Mac, Sean just said, there are still spawning threads.
Next question here.
Hi, hello, I'm here.
Sorry.
Hi there.
Hey.
Great talk, by the way. I've got a question about, can you somehow mark the channel as, I don't know, closed, or mark it as no more values will be sent on the channel, and what happens to a graph when you close the channel?
So when you close the graph, then the no values will be passed anymore downstream, but the graph stays as this until you destruct it.
Thank you.
Okay. So and then design your application so that it can run deadlock free if you have one core or if you have n cores. That's very, very important, because sooner or later, if you design it, for instance, for a 4-core system, or you rely on the fact that I always have 4 cores, then you easily can run into deadlocks. And Sean gave 2 years ago here a presentation exactly about this topic. I just can recommend highly. Yeah, and very, very important. Don't let your application be soaked with mutexes and this stuff. It really hurts your performance. Okay, some people I want to thank for short, my family who supports me in my work. Sean Parent, who taught me lots during this time of the collaboration. My company, who supports my chip here, and all the contributors to the library. I added some kind of reference, which are, I think, are worth reading or looking at. Some books, other libraries which do something similar. That's HPX from Stellar Group. Then there's a CSP framework, an actor framework, and a book by Anthony Williams about low-level details. Some things I highly recommend to view. And, well, that's it so far. And if you have further questions now, or I'm here until Friday morning, so I'm very happy to answer all your questions.
Hello.
Yes. Where hello? There. Yeah, you're just below the light, and I don't see anything in this direction.
I understand. I have a question about the language design, actually, because the problems with futures is, in my opinion, the problem with language design, because, for example, we have async await in C# or JavaScript. So, in my opinion, it's much better and cleaner way to solve the concurrency in code, and it helps with, for example, when you have a promise or future, and then later it's then, and we have a pipe of thens continuations. So my question is, which design do you think? I see you are talking about the channels. So what kind of features do you think?
There was a proposal last year when I was in Berlin that they made the recommendation: why not offer the pipes for using the pipe symbol for the futures as well? And that's something which we already considered, but I did not implement it so far, so that you have a similar structure on both sides. Yes.
And about the async await, there are some kind of.
Well, I think the current design in the standard is, I say it's broken. It's not really useful. Because you cannot specify where the task should be executed, and that's essential. For instance, if you want to update your user interface, you cannot do it. or you have to do some quirks around it. I just see that the time is over, but I'm here to answer your questions.
Thank you very much.
Okay.